still stuck in this house with a mind full of...
We're going to start with RL. And remember what the step response is. The step response is where energy is being added to the magnetic field, so energy buildup. But after a long period of time, the inductor behaves just like a piece of wire. So let's say our circuit looks like this. Here's the resistor. Here's the inductor. There is some voltage across the inductor. That's going to be a function of time. The switch is initially open, but it is closed at t equals 0. And this is our voltage source, so let's say it has a voltage of V sub S over here. So initially there is no energy inside the magnetic field of the inductor. At t equals 0, when the switch is closed, that's when current begins to flow. Now, if you know how inductors behave, if you remember that part, the inductor is initially going to create a back EMF to oppose the change in current through the inductor. So that is going to oppose the current flow, at least initially. However, over time, that's going to die down. The change in current is going to slowly, the current is going to slowly change until it is moving continuously through here, and at that point, all of the current is moving through the inductor, and that current is just I is equal to V over R. So that's, and the inductor at that point is just behaving like it's a piece of wire. Okay, so if we think in terms of KVL here, the voltage across the source there is equal to IR plus the voltage across the inductor, which is L di dt. Okay, now this, at least the right-hand portion over here, this looks very similar to something we've seen before. However, the left-hand portion here is very different. It's no longer 0. Previously, this was a first-order ordinary differential equation. We had L di dt plus IR equals 0, but now we don't have that. Now it's equal to some non-zero thing. So this is now a non-homogeneous. It's a little bit harder to solve. It's not that difficult. I'm not going to go through the steps. Remember, this isn't the differential equations class, but we use differential equations in here. But you can go through the steps to solve that. And whenever you do, you're going to end up with I as a function of time is equal to, and here's where you get a slightly different answer. V sub S over R minus V sub S over R e to the negative t over tau. Now, tau is exactly the same thing. It is L over R. But look at this. We can simplify this a little bit. Let's factor out the V sub S over R. That's going to be 1 minus e to the negative t over tau, like that. So if you were to graph this, let's think about what it looks like here. If we do I of t on that axis, t down here, let's think about what's going on here. At t equals 0, switch is closed. Remember, I said the current is going to be opposed by the back EMF generated by the inductor, and that back EMF is generated because we have a di dt. You cannot have an instantaneous change in current, so this current's got to slowly change here. So the current initially is going to be down here at 0 at t equals 0. Okay, but over time, it's going to rise up, and it's going to approach a maximum value, and then it's going to level off and reach that maximum value in the limit here. Now, if we were to trace that maximum value back to the vertical axis here, that is V sub S over R, like that. Okay, so that's how this is going to behave. Now if you'll think about it, that also should be exactly the way you expected it to turn out, because the current, even though it initially starts out at 0, it slowly builds up. And after a long time, how long is a long time? 5 tau. After 5 tau, this inductor, it behaves just as if it wasn't there. So the circuit behaves as if the inductor wasn't there. There's still energy stored in the magnetic field inside the inductor, but the current is just going to go straight through. So after a long time, 5 tau, the current is essentially V sub S over R. Okay? So that is the step response for an RL circuit for the current, at least. Now, let's think in terms of how that 1 minus e to the negative t over tau behaves. Because we've already made this chart once, where let's say that we have a chart here, and we've said t, and we did e to the negative t over tau. Well, now let's expand that and do 1 minus e to the negative t over tau. And after 1 tau of time, we said this is down to like 0.367 something. But this is 1 minus that, so this is 0.63 something. Okay? And then after 2 tau, this is down to 0.135. This is going to be like 0.86. 3 tau, I'm just rounding these numbers here, and I could round them wrong. Just keep that in mind. 0.049, so that's actually close to 0.05, so that makes this one like 0.95. So it's 95% up to its maximum value by 3 tau. After 4 tau, this is 0.018, which means it's 0.98%. And after 5 tau, we're below 1%, so it's 0.006, which makes this 0.994 approximately. So it's 99% done after that. So it's less than 1% left to finishing. So once again, 5 tau is the time for this term that's in the parenthesis, the 1 minus e to the negative t over tau. It takes 5 tau for that to complete its process as well. Now, let's turn our attention to the voltage. Let's say that we wanted to figure out what this voltage is. We got the current. So what is V sub t, in other words? Well, it's going to follow the same general pattern, but you got to use your circuits knowledge to figure this out. How is that inductor going to behave? Initially, it's got a back EMF right at t equals 0 that opposes the current, that doesn't allow the current through. But then, after a long time, all of the current is going through it there. So if all of the current is going through it and it's behaving like a piece of wire, what's the potential difference across a piece of wire? And the answer is 0. So you expect this to behave a little differently than what the current function looks like. You expect it actually to decay, to be a decaying exponential. In other words, we're kind of expecting this, based upon our circuits knowledge, that the V of t versus t is going to start at some maximum value and then decay over time like that. Okay, but how do you find the V of t? Well, V is just L di dt. Okay, this is what the I looks like down here, so you take the derivative of that. So it's just L times the derivative with respect to time of V sub S over R times 1 minus e to the negative t over tau. So we need to take the derivative of that. Let's see. This first term, take the derivative. I'm imagining this V sub S over R being distributed through. So this first term with the 1 is going to go to 0. Then we're going to have the derivative of this over here. So we're going to have V sub S over R. Now I'm taking that negative sign, put it right there. And we're going to have a factor that's going to be negative 1 over tau times e to the negative t over tau. So right, just like that. Now, if you plug in for tau, remember what tau is. Tau is L over R. If you were to plug in for tau, L over R, you're going to discover that the L's will cancel since this is 1 over tau. And you're going to end up with something that looks like this. The negatives are also going to cancel. You're going to end up with something that, oh, by the way, the R will also cancel here because you've got an R there. So this is L over R, it's going to cancel out. This is going to end up being V sub S e to the negative T over tau, which, using your circuits knowledge, you figured out, yeah, that's what it ought to look like. So having a familiarity with these circuit elements, how they behave when you turn the switch on, and what to expect, like they're either going to rise up and level off or they're going to decay like that. Those are really the only two possibilities here. Either the quantity you're after, voltage or current, is going to rise up and level off, or it's going to decay over time. So that's really the only two possibilities. Let's very quickly look at an RC step response as well, now that we've got all that under our belt here. Okay, initially this is an incomplete circuit, so there's no energy going over here to the capacitor. Initially, all the current is just over here in the resistor, right here. You could figure out what the voltage is if you knew what R was and what I sub S was. You could figure out what the voltage was across that resistor right away. But there's no energy stored in the capacitor, so nothing is there before t equals 0. However, at t equals 0, the switch is closed. Now, at t equals 0, then, when you get to this junction, when the current comes around and it gets to this junction, then it has a choice to go down this way or to go that way after that switch is closed. Well, all of that current is going to go down this way. And the reason is because there is nothing opposing it over here. Remember how the capacitor creates a displacement current across its plates. The current comes in, builds up a charge on one plate, which induces the charge on the other plate, so it looks like that current is passing right straight through. So at least for the fraction of a moment, right after t equals 0, all of that current's going to be flowing over here. Now you can do that. You can have an instantaneous change in current for the capacitor. You cannot have an instantaneous change in voltage. Okay? So you've got to keep that in mind as well. So let's go through the steps here of looking at what this equation is going to look like and try to find the equation of state, the first order differential equation for this circuit. Okay, what we're going to do, the way that we're going to do it is we're going to sum the currents away from this top essential node. So I've kind of messed it up here. So let's say there's the top essential node there. I'm going to imagine a current going that way, a current going down this way, and a current going that way. So this is essentially node voltage at that point. Well, the one going to the left, that's going to be negative I sub S. Okay, the one going down the bottom, I'm going to call this node voltage here. Well, the node voltage here is going to be the voltage across the capacitor. Because if I call this my ground down here, then that node is going to have the same voltage as the capacitor. So that one is V sub C over R. That's the current going down the middle. And now over to the right-hand side, that current is going to be C dV sub C dt. And now all of that's equal to 0. So that came about because of a node voltage equation. I'm going to rearrange the terms just so it looks a little easier to read. Now, this is our first order ordinary differential equation. That's the equation of state for this circuit here, with this RC circuit. This is, again, a step response. So how do you solve this one? Well, same sort of way. You can go through the possibilities or through the process of solving this if you want to. I'm just going to jump to the solution here. V sub C as a function of time is equal to I sub S R plus, parenthesis, V naught, that's V at 0, minus I sub S R e to the negative t over tau. And since this is an RC circuit, tau is just equal to RC, like that. Okay, so once again, we've got something that looks a little similar. Now, you see that V naught right there? That came about when you tried to solve the circuit here. That's the initial voltage that's on the capacitor. And you may have seen something similar that's, if we did like I dt plus V naught, that's the voltage. You've seen equations like that. Okay, well, that's that V naught. That's where that came from. That's the initial voltage across the capacitor. But for our example here, that is 0. So V naught is 0 for our capacitor. So this reduces down to that's what it looks like. Now, you can factor out the I sub SR, and I've got 1 minus e to the negative t over tau, once again. So this one is going to look very similar. I've got my V sub c versus t, starts off at 0, rises up, levels off to some maximum value in the limit, and that maximum value is going to be I sub SR. So that's the voltage across the capacitor. Now, what if I want to find the current? What if I want to find this current going through the capacitor there? Okay, well, I equals C dV dt, and that voltage is the voltage across the capacitor. This current is current through the capacitor. So you just take this, you take the derivative of it, and you've got the equation for that. Now, what do you expect that to look like? Remember what we talked about at the beginning. All of the current is going to pass through here initially, which is going to build up a very slow increase in the potential difference between these capacitors. And when I say very slow, I mean within 5 tau, it's going to build that up. So it's going to quickly increase the voltage across this, but the current initially is going to be very high. So what do you expect the current through that capacitor to look like? Well, I expect the current to look like I sub c t, starting high and going low, like that. In fact, I expect that to be I sub s, all of the current to be going through that capacitor, at least at t equals 0. Well, I'm going to leave it as an exercise to you to take this equation, take your V sub c that you've got down here at the bottom, and take the derivative of it, multiply it by c, and you're going to discover exactly what you end up with is I sub c is going to be I sub s e to the negative t over tau. That should be exactly what you end up with. All right, so what we've done now is we've gone through all of these natural and step responses for both RL and RC circuits. Now what I want to do is turn our attention to a more general approach, because you have probably noticed that there are patterns present in every one of these. And those patterns are going to allow us to figure out more general solutions that are going to apply. You may have also noticed that the solutions are very similar to each other because the differential equations are very similar to each other. There's really only 4 possible ways to arrange these simple RC circuits and RL circuits. Let's say that, well, in fact, let's draw all four of them. You can have an R and an L like that. So you can have an R and an L with some voltage there. You could also have a situation like this where maybe you've got an L here, there's your R, and this is some I. Now, these two circuits, you may notice, are equivalent to each other. If you think of that being the terminals, then what's on the left-hand portion there of the pin is the Thevenin equivalent. So you've got a VTH and an RTH, and the load here is the inductor. But you could do a transformation, a source transformation on that, and this is ISC, which is the same as VTH over RTH. So that is the Norton equivalent. And here the resistor would be RTH, and once again, these would be the terminals. So you've got the inductor as the load on either one of those two cases right there. Now, let's say that you've got, let's say, a capacitor now. So capacitor, once again, you got some voltage, you got a resistor, you got your capacitor. Once again, this is a Thevenin equivalent. Or with source transformation, you can get the Norton out of it. And that's, once again, is ISC. And this is RTH. Okay, so really, you've got four possibilities here. Now, in each of these cases, you're probably going to be interested in whatever the voltage is across the inductor, or whatever this current is, or the voltage across that, and whatever this current is here, or the voltage across this guy and whatever that current is, or the voltage across the capacitor there and whatever that current is. So you're going to be interested in those currents or those voltages in all of those cases there. Okay, for each of these equations then, there is a pattern that is evident. All of the equations of state reduce down to this. Let me show you. dx dt, and x is either going to be the voltage or the current that you're interested in, plus x over tau equals, and that's supposed to be a kappa, Greek letter kappa. Okay, now you might say, well, I'm not seeing that. Well, think back. You had dv dt plus r over lv equals 0. Okay, that was the equation for the natural response for an RL circuit. The v is x. The v is x here. The tau, you notice that's tau on bottom. Tau is L over R for an RL circuit, so it's 1 over that, so we got R over L here. And the K happens to be 0. The K happens to be 0 because it's the natural response. However, if we did that same sort of thing for the capacitor, then you're going to have di dt plus I over RC. That's equal to 0. So there's the natural response for the RC. And then the step response equations looked, I guess, pretty similar, except you're not going to have the 0 over here on the right-hand side for each one of these. So if you're talking about the RL, we set it up so that we had this equation as our equation of state, plus R over Li equals V sub S over L, or for the capacitor, the step response was dV dt plus V over RC equals I sub S over C. So down here on bottom, these are the step responses. These are the natural responses, and this is for the inductor, and these are for these two over here are for the capacitor. So we've got a tau value and we've got a K value here, or a kappa value for each one of those. Now, if you pay attention to this and you spend some time with these equations and you start seeing patterns in here, in each case, the X is going to be either V or I. I think that part is obvious. But in each case, that X approaches a constant value. So in the end, in the limit, the X is going to be 0 or it's going to approach the constant value. Remember, in some cases, we had the rising leveling off exponential, and in other cases, we had the decaying exponential. So it's going to be one of those. It's either going to in the limit go to 0, or in the limit level off to some maximum value here. So that final value, that let's call that X sub F, that's X final. In each case, if you know which one of these cases you've got, the x final is always going to be the kappa times the tau. Okay? So that's the final value, always. Okay? That means that in each of these cases, you can solve these equations. In fact, you could even use this general form right here and go through the process of solving it. And here's what you would end up with. I'm going to get another sheet of paper here. I'll just use the back side. Okay? And you're going to end up with a generic solution that looks like this. X final plus x at t naught, and t naught is the first time when the switch is closed, minus x final times e to the negative t minus t naught over tau. Okay, so this is the final value. This is the initial value. And once again, that's final. And t naught is the time the switch is thrown. That could be t equals 0, but that's the time the switch is thrown. That's when you start making the observation. And then tau here is the time constant. Okay, so everything that we have just done, we've spent, what, 3 videos going through or maybe it's 4 videos by this point, I don't know, going through the natural and step response for all of these various RL and RC circuits. But it all boils down to this is your solution. So really, this is all you need to know. So if you want to find the natural and step response for an RL and RC circuit, then all you have to do is identify what variable you're interested in. Are you interested in I or are you interested in V? Okay, figure out which one of those you're interested in because that's going to be your X. All right, then determine the initial values. So determine X at T naught. Now that could be X at 0. We've sometimes called it X naught or V naught or I naught or I sub S, whatever it is. That's the initial value. Whenever the switch is thrown, that's the initial value right there. That X sub F is going to be kappa times tau, though. You're going to need to calculate tau, so tau is going to be either RC or L over R. But then, once you've got these things figured out, once you've got these initial and final values figured out, then you just plug it in. And oftentimes, you don't even have to do any calculations here. You can, like I said, using your circuit's knowledge, you can almost, just by inspection, figure out what the final value of X is going to be, or what the initial value of X is going to be. And then, almost immediately, jump to the solution. Now, let me show you an example of us being able to do that. So that's called the general approach, and we're going to use the general approach here. All right, here is our problem. Previously, we had to go through finding the differential equation, the first order differential equation. Then we had to go through the steps of solving it, and then we figured out, and I will just show you what the answer it was in those cases. V sub c of t is going to be I sub s times r times 1 minus e to the negative t over tau, and tau in this case is just going to be RC. Okay, so we know that that's the answer right there, but let's use our general approach and let's try and figure out what the answer should look like. Remember, here's the general approach. X of t is equal to x sub f plus x, let's call it t naught, minus x sub f times e to the negative t over tau. So this is our general solution. We need to figure out what we're interested in. Well, we're interested in x sub c. So I'm sorry, v sub c. So v sub c is what x is. Okay, that's the first step. Now let's figure out what v sub c at 0 is. That's the initial value. Well, V sub C at 0, since the switch is open before t equals 0, that's going to be 0. Okay. Okay, so that's the next step. What about V sub C at infinity, at time infinity, as t goes to infinity? In other words, what is V sub C final? Okay, well, that's going to be kappa tau. All right, well, what is kappa here? Well, in order for you to remember what kappa is, you're going to have to look back at the differential equations, and it turns out that it's I sub s over c multiplied by tau, which is RC, so it's just I sub s r. In other words, the final value for the capacitor is just going to be whatever the voltage is across this thing right here. That's the final voltage. Okay. Now now you did not have to go through this to figure that out. Your circuits knowledge should have been able to tell you that this final voltage across this is going to be the final voltage across that resistor there. Well, what's the final voltage across that resistor? It's just I times R. It's I sub s times R. So that's your final value. Okay, so that's your X final, or your V sub C final. Okay, then what about tau? Well, tau is going to be RC in this case. So we're ready to apply that right there. V sub C at T is equal to X final. Let's see, where was X final? That's just I sub S R. I'm sorry, plus, let's see, what is the initial value? The initial value was 0, minus the final again, I sub s r, times e to the negative t over tau, which is just RC. Simplifying it, I sub s r is 1 minus e to the negative t over tau, where tau equals RC. There's our answer, which matches that right there. Okay, so you can use the general approach here to get to the same solutions that we did. So that equation right there, if I were you, I would commit that to memory, because you're probably going to use it quite a bit. Now, let's follow through on that. Let's say that I wanted to find the current, this current here. Okay, well, you use the same equation. You don't use a different equation, you use exactly the same one. All right, I want the current, so that's just going to be I sub C. That's what I'm interested in. So I sub C of t is what x is. So let's write that down. I sub C of t is equal to I final. Now, what's I final? What's the final current going to be over here? Well, the final current is going to be 0 after this thing gets charged up. So this is going to be 0 plus, okay. Now, what about the initial current? The initial current, well, that's just going to be I sub s. Sub s minus, and we're back to the final again, 0. Times e to the negative t over tau. So what does that tell me? That tells me that I sub c t is equal to I sub s e to the negative t over tau. There. So you can use this same technique on any component where you have, or any type of circuit where you have one R and one C. However, in reality, you're going to have multiple R's, you're going to have multiple C's. So what we need to do is we need to go through an approach so that we can figure it, so that we can, I guess, wean it down so that we only have one R and one C. If we can do that, then we can use this general approach right here and with no problems, okay? And we'll do that in just a minute, okay? In the meantime, I want to show you something else. Let's say that we've got a op-amp. One feedback resistor. This is the resistor that's in series with the source here. What is that? That's an inverting op-amp. So it's an inverting op-amp. Now, here's what I'm going to do. I'm going to take that and I'm going to replace it with a capacitor. Okay? And I'll redraw that on a clean sheet of paper here. Let's solve this one. Well, using the techniques that we know, V sub P equals V sub N, and I sub P equals I sub N equals 0. Well, this is V sub P, and you see it's going straight to ground, so we know that V sub P is going to be 0. So that means this V sub N is also going to be 0 here. Okay, we know that. We also know that these currents going in here, that's I sub N, this is I sub P, that those are going to be 0. So we just know that by inspection. By inspection, V sub P equals V sub N equals 0. All right. Now, at the V sub N node, then we use our regular technique of node voltage equation. So V sub N minus V sub S over V sub S plus, now the current going this way is C sub F times dV dt. But this V here, this V is equal to V sub N minus V output, like that. Okay? So this is the derivative of that right there. So the V sub N, that's 0. This V sub N, that's 0. And what are we left with? Minus V sub S over R sub S. How did that get on bottom? That's a mistake. R sub S. That should be R sub S. Thank you for pointing that out. I just got that message. Okay, plus, I'm screwing up here, minus C sub F dV naught dt, and that's all equal to 0. In fact, all that's equal to 0 as well. Okay, so we got minus signs on everything. We'll get rid of that minus sign. Just rewrite it one more time. V sub S, R sub S, plus C sub F dV naught dt equals 0. Okay, now we've got once again a first order differential equation. We should be able to solve that, but really remember what we want to do here. We want to write the output in terms of the input, and once we've done that, we've solved this op-amp problem. So let's do separation of variables for this here. I'm going to leave dV naught dt on one side by itself, and let's put everything else on the other side. So I'm going to have a minus V sub S over R sub F, and I'm going to divide by the C sub F, so C sub F. So you notice what I've got over here. That's V sub S over what is effectively the time constant here. Now what am I going to do? I'm going to integrate both sides, and let me just move up here for that. Whenever you do that, on the left-hand side here, you're going to end up with V naught as a function of time. Now, we're going from that initial time, T naught, to some later time, T. So it's actually going to be V naught minus V naught at T naught. And that's equal to this stuff over here on the right-hand side, which is minus the integral of V sub S over R sub S C sub F dt plus, no, that's all. That's all right there. So when it comes to V naught of T, that's equal to minus the integral V sub S over R sub S C sub F dt plus V naught at T naught. Okay. Now, look at what we've got here. This says that the output is the integral of the input. Now it's a scaled integral because of these constants down here, r sub s and c sub f. You could factor those out of the integral though, and this is just the integral of the input, plus whatever the initial voltage was at t equals 0. Okay. Now that output may have been 0. There may have been no voltage initially over here on the output, in which case that would have been 0 right there. But what do you think this one is called? This is an integrator op-amp. It's an integrating amplifier because you're going to get out the integral of whatever the input was. And well, you might say, well, how does that work? Well, if you, let's say you input a step function. So let's say the v sub s versus time, you do some kind of step function, and it makes a transition down at point at time t1, and then it goes over here, goes back up, and let's say the entire period of time is 2 t1. So it starts here at 0, it goes up to the maximum value of v sub m, and then it goes to some negative value down here, which is going to be minus v sub m. Okay, so that's what the source is doing. Okay, well, what should the integral function look like? In other words, what's the output going to look like for something like that? Okay, well, this is the output, just bringing that time t1 down here. There's that time 2t1 right there. This is the t-axis. Okay, well, what's that going to look like? Well, remember, it's going to be inverted to begin with, so it's going to look something like that, because we're taking the integral of that thing, and the reason it's down here is because it's negative, but then right here it changes and does something like that. So I would hope that you would be able to figure that out. If you need to do the math to see that, then the V output of t is going to be minus 1 over RC of the integral of whatever the source function is, dt, plus V naught at t naught. And you're going from t naught to time t here. So what are you doing? You take this function here between 0 and t1, and take the integral of it. Okay, well, it's a constant, so when you integrate that, you're going to get a variable function in it. The negative sign is going to bring it down here, so it's going to be like that. And then over here, it's going to be like that. I'm assuming that this is 0. My advice would be spend a little time with this. See if you can work your way backwards here. This one has a slope that is downward, so the derivative of this is going to be a constant. So it's a linear downward here. The only reason that it's below the line here in the negative region has to do with that negative sign right there. Okay, we'll stop right there for today, and then we'll work some more problems with using the general approach, and maybe we'll talk about some other things as well. Okay.
Still stuck in this house with a mind full of doubts. Tired of staring out the window. Eating too much, drinking too much. Tired of watching the grass grow. Channel 2, Channel 3, back to Channel 2. I watched everything in my queue. So put me on a train, I don't care where it's going. Fly me on a plane, maybe out to Wyoming. Need an RV, no plans, just you and me. I need to go somewhere. Still watching the rain, kids driving me insane. Another Groundhog Day routine. Stuck in my head, existential dread. What in the world does it mean? Month 2, month 4, can't take it anymore. I got to get my feet out the door. So put me on a train, I don't care where it's going. Fly me on a plane, maybe out to Wyoming. Need an RV, no plans, just you and me. I need to go somewhere. I need to go somewhere. minivan, skateboard, cruise ship, submarine, DeLorean, on a horse and a Porsche, on a boat with T-Pain, swim like a mermaid, maybe all the way to Spain. Listen, Karen, I'll even ride on my rollerblades. I need to go somewhere. I need to go somewhere.